So for this video, I'm going to suggest two things right now. Pause the video, well, don't pause yet, but in a second, pause the video, adjust the play speed to at least 1.5 times, because as the title suggests right up there, optional, okay? This is the relevant application of all the stuff that we just studied for this particular unit, boils down into proteins, primary structure, and this kind of fun stuff. But because it's optional, double speed it. To that same extent, it is kind of optional. So don't stress about this content. If I put an exam question in based off of this, it will provide a lot of that secondary content that would allow you to answer the question without having seen the video. Okay? But seeing the video might make it easier. I don't know. The other thing I want you to be aware of is you should take advantage of the pause to go through and read what's on the slides. These are literally the textbook slides because it's kind of outside the scope of the class. So while it's super relevant for biochemistry, it's borderline relevant for what we're doing in organic synthesis. Okay, so a little outside the scope. So first and foremost, if we're going to move into biochemistry, we're going to study the building blocks of the primary categories or the primary groups of biomolecules. One of those being proteins. And proteins are made up of amino acids, as we have kind of addressed in the past. We have the amine portion, and then we have, we'll dot that out, the acid portion. When I take two amino acids and I react them with each other, so amine and acid, and I take another amine with an acid, that amine can come in, do a nucleophilic addition, followed by the elimination, and then some acid-based fancy stuff in between, and what we now have would be a protein. In that case that I just deleted, a dimer, because we had two individual amino acids. Proteins have their own language associated with them, and that's something you would learn in a biochemistry class. The textbook is referencing it here with the N terminus and the C terminus, and that's just kind of our default way of looking at the amino acid for how we sequence our proteins. Why this becomes important for biochem is that if we're trying to study a protein, we need to know what amino acids would into it. So we could take the protein and then we could start cutting it apart. But because each of those amino acids have the same linkage, that amide linkage, we're going to get random kind of cuts. Okay? So we could go through and completely destroy the whole thing, as the synthesis is suggesting here, with acid, significant amount of time and a significant amount of heat to kind of cleave all of those bonds. That would give us the amino acid composition, but it would lose a lot of information too. I wouldn't know the sequence those amino acids were in, for instance. I would just know that they were there. Okay? So what I would want to do is be a little bit more selective in how I break apart that acid derivative amide bond, and that selectivity, of course, is now going to require someone to be creative to create something that selects for a specific location. And that's where we encounter the Edman degradation. Okay. Yeah, which we'll address in a second. So the kind of core tenets of this, you're going to start with phenyl isothiocyanate. Okay, and the point of that is that that's going to activate our nitrogen and now bring around some chemistry of the thiol to help kind of separate the amino acid, one amino acid at a time, away from the protein. So we're attacking the N terminus of the amino acid or the protein and slowly start pulling off amino acids and evaluating those pieces as they come off, okay? Which is neat. Okay, we get the sequence. Yay, sequence. That isn't that the same thing? No, we're doing some slight variations behind this. We're pulling off each of the pieces, breaking it all apart so that we can get to the individual derivative components. The R group is what changes for each of the amino acids. So this PTH derivative, once this has come off, I can now evaluate it and decide based off of certain properties, because there's only 20 amino acids, what amino acid that was, because the R group is going to change the intermolecular forces, allowing me to identify it. Okay? But that's not really practical if you have more than 30 amino acids, as suggesting here, because here's my protein, I cut one off, I analyze the piece. I cut the next one off, I analyze the piece. The next one, piece. Okay, so that's a very tedious and time-consumptive process because you're breaking each of those individual pieces off as you go through and do this. So if you're clearing 30 amino acids in your protein, that's a lot of analysis. Okay, so what you can end up doing is breaking apart the protein sequence into smaller chunks and then evaluating those smaller chunks. Once you have the chunks, you can try and determine the sequence in the chunk and then start linking the chunks to each other. Okay? That does require that we have to know when and where and how and why your amino acid sequence is getting cut. Okay? And we would need particular enzymes or functionalities to allow us to do that. But that's what biochemistry does. Right? They have found things that work very well, and that's what they end up using. Right? If we wanted to reverse this process, which is actually becoming increasingly common, because we know proteins do really cool things, but at the same time, they aren't designed to do just that thing. They also have to interact with their environment and find those pieces. So if we limited the extraneous stuff that that protein had to see, right, or do, or fit into, then we could potentially synthesize a synthetic amino acid or a synthetic protein that only does that thing. So just where the chemistry is happening, we just have that piece and we get rid of everything else. But that means we have to come in to synthesize it. Okay? So the synthesis of the protein is now connecting each of the amino acids with each other, and you have to connect them in a very particular order. Okay? DCC is a reagent that helps to facilitate that linkage between the amine and the carboxylic acid. The structure of the DCC is shown below, and as you might start to note, you've got some polar pi bonds within that. Okay. We've got polar pi bonds, and we have lone pairs on our nitrogens. That gives us a variety of chemistry that we could try to take advantage of in a potential synthesis. Okay? So DCC, lone pair, remove the hydrogen to activate our carboxylic acid. Okay? The acid can now attack our DCC. Right? That's a relatively minor or weak nucleophile because of resonance stabilization of that carboxylic or carboxylate, but DCC, due to that vast polarity of that molecule, is susceptible to that attack. Okay? So DCC facilitates that. Now we can bring in our amino acid or the next amino acid we want in our sequence. That will then attack the carbonyl carbon, and we get the elimination of that big old nasty DCC piece, which is now oxidized. Actually, it's not oxidized because we lost 2 nitrogen pi bonds and we gained 2 bonds to oxygen. So we didn't really oxidize it. We just changed where the oxygen was located. Okay. Cool, I guess. If you really wanted to drill into it, it's there, and I would recommend looking at it at least. Okay. So DCC is really good at coupling amino acids, but as this is also suggesting, remember the amino acid, when we're doing the synthesis, we're doing it in a solution of probably hundreds of thousands, if not billions of molecules, which means that initial amino acid we're starting with, we may be trying to target the acid side of it, the amine is still floating around. that amine could potentially mess with the synthesis. So we would need to incorporate protecting groups to minimize some of the kind of cross-contamination as the synthesis is suggesting here. If I mix alanine and glycine with DCC, I'm going to get both sequences, both alanine-glycine and glycine-alanine. And for that matter, glycine-glycine and alanine-alanine. Some of that can be controlled a little bit with concentrations and when you're putting species in, but without those protecting groups, it's going to be a mess. Okay? So protecting groups, yay, more things you could throw in there. So our benzyl chloroformate, it's just a name, it's just a thing. It protects the amine. Okay? The benzyl alcohol can be used to protect the carboxylic acid. The alcohol one, this one, was actually already addressed in that protecting group video just a little while ago, that last video you watched. Okay. So peptides, we go through, we protect each piece, we do the coupling, we make our dimer, we deprotect, we protect potentially again so that we can go through and do the next amino acid. So it's a lot of on, off, on, off, on, off, on, off, on, off. It's not a really efficient way of going about doing it, and this is why we try to get enzymes or bacteria to do it for us, okay? And we train them to go through that process. And train, I'm sure, was a horrible word for that. Blame the biochemist that died inside me a long time ago. This could be improved if we move to the Merrifield synthesis. Again, all we're trying to do is control some of that reaction cycle so that we can increase efficiency. It's carboxylic acid derivative all the way through. Okay? And it's just a question of what you're protecting versus what you're not, and the sequence in which you run those things. Okay? So yeah, I mean, yay. In this case, if you attach it to the bead you can isolate easier, more physically, because it's a solid chunk of bead, and that can make it easier to keep kind of pulling your protein out of the reaction cycle so that you can put it into the next one, and into the next one, and into the next one. And that's cool. Once you've got your protein sequence, then you go through and remove the bead. So the bead served kind of two purposes. One, a physical separation ability, and it also acts as a protecting group for that other half. Looks like the acid side of our amino acid. And with that, we're done. So that wasn't too horrible. If you watched it at double time, you're under 10 minutes. Good on you. And that's all I got. So good luck on the exam, and we'll meet again for a lecture with our aromatic rings next unit. Have a good rest of the day.